What is the maximum number of electrons that can occupy each of the following subshells? The 3p, the 5d, the 2s, and the 4f. Okay, there's a relationship between the angular momentum quantum number and the ML number, the magnetic quantum number, the orientation number, in other words. So if you're a zero shape, there's only one orientation, a zero orientation. When you have a 1 shape, there's 3 orientations, a -1 orientation, a 0, and a 1 orientation, an X, Y, and Z. When you get to the 2 shape, there are 5 orientations, a -2, a -1, a 0, 1, and a 2. And when you get to the F shape, there are 7 orientations. So when we're dealing with a 3p, there are 3 orbitals representing those 3 orientations. So each of those orientations can take 2 electrons. So I can put 1, 2, 3, 4, 5, 6 electrons in the 3p. When I'm dealing with the 5d, right, each of those orientations, those 5 orientations of equal energy, I should say, can take 2 electrons. So I can put 1, 2, 3, 4, 5. And then I start backfilling 6, 7, 8, 9, 10 electrons in the 3D. The 2s, you can take 2 electrons, right, for the only 1 orientation. And in the 4f, since there are 7 orientations, I can put 14 electrons into the 4f. What are valence electrons? Okay, when we look at an electron configuration for, say, nitrogen, 7 protons in the nucleus. The 2 electrons can fit in the first energy level in the S shape. 2 electrons can fit in the 2s of the second energy level. And in the second energy level, you introduce a P shape, all right, where each of them would be half filled according to Hund's rule. Core electrons are inner electrons, right? So a way of writing this is to say that the 1s electrons represent a helium configuration on the inside, and the valence electrons are on the outside. Oh, B, what are core electrons? Oh, there they are. So the core electrons are on the inside, shielding the outer electrons from filling the nucleus. What does each box in an orbital diagram represent? Well, a place where electrons can go, 2 electrons per box. What is the quantity represented by the half arrows in the orbital diagram? Again, 2 electrons can fit in a space. So 1 space in the first energy level, 4 spaces in the second energy level. What is wrong with the following electron configurations for atoms in their ground states? Okay, so ground state. Electrons can be anywhere when they're in their excited states. So if I'm looking at an electron configuration 1s2, 2s2, 3s1, we're skipping electrons going into the 2p. All right, so the 1s fills, the 2s fills, and part of the second energy level is a P shape, higher potential energy shape, but nonetheless part of that second energy level. So electrons would go into the 2p before they would go into the 3s. B, neon core, 2s2, 2p3. All right, so yeah, this is just wrong. A neon core is the 1s filled and the 2s and 2p filled, right? So this would be a neon configuration. So you don't have that with this electron configuration. The mistake here must be that you're talking about a helium core. So the 1s electrons would represent the inner electrons, and the electrons in the second energy level would represent the valence electrons. Right. C. Neon core 3s2, 3d5. Okay, so we got a neon core 3s2. Right, electrons start going into the 3p and then they go into the 4s before you start putting electrons into the 3d. So both of these orbitals, even though the 4s is on the outside, because of its shape, because it's a more penetrating shape, you put electrons into the 4s before you put electrons into the 3d. Again, cloverleaf shape, even though it's on the inside, is a higher potential energy shape than the 4s. So this would be the electron configuration. The 3p filled, 4s filled, and then you start putting electrons into the 3d.